Alright everyone, hello. This is the video that fills in for the content review session number 14. So we're going to jump straight in. We're going to quickly review what we did in content review session 12, I believe, or 11 actually. 12, I don't remember. Where we talk about carbohydrates, chapter 24. So carbohydrates are polyhydroxyaldehydes or ketones, which means that the carbon chain, the main backbone carbon chain, must have multiple hydroxy groups, as we can see here, and one aldehyde or one ketone at least. So things such as this alcohol, this triol, aren't a carbohydrate because they don't have an aldehyde or a ketone. This carbon chain right here is not polyhydroxy, it only has one hydroxy group, so that's not an aldehyde or a ketone either. So when we talk about carbohydrates, we talk about the classification of carbohydrates. We can classify them multiple ways. One way being by talking about how many carbons they have. So if it has, as we see here, 1, 2, 3, 4, 5, 6 carbons in the Fisher projection, we call this a hexose. If it has 5, we call that a pentose. So we can classify them by how many carbons they have. And we can also classify them by the kind of carbonyl they have. So some of them will have aldehydes, we call those aldoses. Some of them will have ketones, we call them ketoses. So this, for example, over here will be a 6-carbon aldose. This is a 6-carbon ketose, etc., etc. One of these, so this right here, this structure, is what we consider to be, so this structure right here is what we consider to be, it is the single unit of a carbohydrate, and it's called a saccharide. So we call a single unit a saccharide. So if I have one saccharide like this by itself, it's called a monosaccharide. If I have two of them linked together, it's called a disaccharide. If I have multiple of them linked together, it's called a polysaccharide. So moving on down, we're going to talk about the main saccharides, or the main single units that we will be discussing in CHE118C. We have here in the middle glucose, mannose, and over here on the right fructose, and we talked about the stereochemistry of the three. Remember that if I have two compounds that are mirror images of each other, as we can see here, all the OHs and the H's on this side line up, and all the OHs on this side and that side line up, as well as the hydrogens. So that means they're looking at each other in the mirror technically. These are called enantiomers. This is called the D enantiomer, that's called the L enantiomer. We're mostly going to be focusing on the D enantiomer because that's the ones that, the D configuration are the ones that are found most in biological systems. So mirror images, complete mirror images, are called enantiomers. A diastereomer is what we consider when two molecules aren't complete mirror images, but they mirror each other in some aspects, as we can see over here at the bottom of this molecule. So at the bottom of these two molecules, they look pretty much identical. But on the top, we see that this portion right here, and this portion right here, they're mirrored. It's flipped. So these are called diastereomers, and these are diastereomers at the 2 and 3 carbon. And then a special kind of diastereomer that we discussed that's specific to sugars is called the epimer, which is the diastereomer at 1 carbon. So over here we see that at carbon number 2, right here, carbon number 2 has the mirroring happening here, and then the rest of the molecule is exactly the same. So this we call it a C2 epimer, and that helps us relate these three saccharides that we're talking about. We start with glucose. We look at glucose and we say that, okay, mannose is a C2 epimer of glucose. So the rest of the molecule is exactly the same, but the only thing that differs is this carbon number 2, C2, and we have the numbers 1, 2, 3, 4, 5, 6. Fructose is a C2 isomer of glucose, meaning that they have the same chemical formula, they just don't have the same chemical structure. So they're both C2H12O6, but here we have the carbonyl at carbon number 1, and here we have the carbonyl at carbon number 2. So how do we draw glucose? So when trying to remember these three, remember glucose first, and then remember the relationship that mannose and fructose have to glucose. So how do we draw glucose? Well, draw the aldehyde on the top, draw the aldehyde on the top, draw the CH2OH at the very bottom, carbon number 1, carbon number 6 taken care of. This 5 carbon will always be on the right side, so it'll always be here, so draw it like this. And then we draw this triangle here, where this dotted line over here corresponds to the carbon chain backbone, and this triangle and these dots correspond to where the OHs fall. So here we see at C2 have an OH on the right side, at C3 an OH on the left, and at C4 an OH on the right. So that takes care of carbons number 2, 3, and 4, and that is how we draw our glucose. So we've been showing all of these sugars in their open chain form, but the fact of the matter is that the sugars actually exist largely in a ring form. We talked earlier in the quarter about how if I have a carbonyl and I have an OH a few carbons away, I can get intramolecular reaction. The OH attacks the carbonyl, and then I get this, ring structure here, where firstly, well, now I can say that the same applies to sugars, same applies to glucose. I'm going to draw my glucose using this triangle method here again. I drew the glucose, and in the intramolecular reactions for glucose, mannose, and fructose, here's what happens. The OH on carbon number 5, it'll always be the OH on carbon number 5, will attack the carbonyl. So it'll attack the carbonyl up here, or if the carbonyl is down here for a fructose, it'll attack that carbonyl as well. So the O becomes part of the ring, and then I draw the rest of my OHs and such. So how exactly do I draw it? So here's a convention that I've come up with. If in my straight chain carbon, so I draw my straight chain glucose, in my straight chain carbon, if I have anything that is on the right side of this backbone, everything on the right side of the carbon points downward. Anything on the left side points upward. So let's see. I'm going to take my C5 and I'm going to connect it to my C1. So take my C5 and then connect it to my C1. So this is the C5, this is the OH on the C5 right here. So this is the C5. This is the OH on the C5. It's going to bond to carbon number 1. I'm going to make this group, the CH2OH group, I'm always going to point it up. I'm always going to make it point upward on my ring. So this CH2OH is always going to be pointing up, and we see that the CH2OH is connected to carbon number 5. And then I just go down the list. Okay, so carbon number 4, OH is on the right, so it points down. OH is on the left for carbon number 3, points up. OH is on the right for carbon number 2, points down. And then carbon number 1. The issue with carbon number 1 is, does it point up or down? So I have this OH bonding to the carbonyl here, and this will open up the carbonyl, and I'll get an OH forming over here. But so I open that carbonyl up, so it'll be like this. This is the rest of the chain, and this is the OH. Now it opened up, as we can see up over there, up top here. But does this OH point up or down? The answer is it points both up and down. So it can both point. Here we see up and down, and we call these two, this is another way of classifying glucoses. On the left hand side over here we see this is called the alpha glucose. The alpha glucose has this OH pointing down, the beta glucose has the OH pointing up, and these are called the anomeric carbons, the anomeric OHs. These are called anomeric OHs because these two structures are related to each other by the term anomers. They are anomers of each other. And this process of switching between the glucose, the alpha glucose and the beta glucose is called the mutarotation process. It's called mutarotation. So I can be straight chain, go to alpha, go to straight chain, beta, straight chain, alpha, back and forth, back and forth. So we see here that 66% of the time it's in the beta form, 33% of the time it's in the alpha form, and that is because, see these two OHs in the alpha form, they are close to each other. They're steric hindrance, whereas in the beta form they are opposite of each other, trans to each other. There's less steric hindrance. An easy way to remember the alpha is that alpha looks like a fish underwater, means that the OH is down, and for beta that means it's a balloon, it's floating upward. With that being said, we move on to, and then here in class I drew an example of drawing fructose, because fructose is the one that's a little bit funky because it actually makes a 5-carbon ring or 5-membered ring instead of a 6-membered ring as we see here with glucose. So for fructose over here, again, it's the same concept. Carbon number 5, OH number 5 will always be doing the attacking. It'll attack the carbonyl. So OH number 5 over here will be attacking the carbonyl. So that's the O from the OH. This is the CH2OH right here on member number 4. I drew member number 4 here. It always points up. That's the OH right here where I labeled number 5. And then I move down. So here, what I have labeled number 3, this is actually carbon number 1, 2, 3, 4, but I have it labeled number 3 as in it's the the third member in the ring. So this over here will be pointing down because it's on the right hand side. On number 2, it'll be pointing up because it's on the left hand side. And then I get to this number 1 member, the number 1 member right here, which is a little bit tricky because it can sometimes point up and sometimes point down. I need to erase this. How do I do that? Oh well. Anyway, so it'll sometimes point up and sometimes point down. And that's based on whether this carbonyl, the OH, opens up or down. So if the OH opens up, then that means that I get an OH up and a CH2OH down. If the OH opens down in the alpha form, so this would be the beta form, this would be the alpha form. So if the OH opens up down, that means that the CH2OH opens upward. All right. So moving on from that, we get into the main reactions of monosaccharides. This is where we stopped last time. The main reactions of monosaccharides, the first one that we talked about was the epimerization, which is going from glucose to fructose to mannose to glucose and blah, 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 back and forth. We can go through all of them between each other, the epimerization and isomerization. All we need is base and water. So I showed an example starting off with fructose. So I took fructose and I labeled this bottom part R because this bottom part's kind of irrelevant for this mechanism and I didn't want to draw it over and over again, so I labeled this bottom part R. This is fructose right here. This carbon over here is an alpha carbon, as we can see, and so is this one. And alpha carbons, we know that they're relatively acidic. So if I have base and I have an acidic hydrogen, I can deprotonate, and I said that I'm going to deprotonate this one as opposed to this hydrogen because this hydrogen is less accessible. It's harder for the OH to try to swim in. See this OH, if it has to try to like swim in over here and pull off that proton, as opposed to if it was going to try to pull off the proton from the very top, it's much easier for it to do that. So it's more accessible. That is why it's going to pull off that proton. And when we pull off a proton from a carbon, we know that we form a carboanion, and then this carboanion can resonate through resonance and form the double bond right here in the middle. You can form that double bond, and this O can pick up a hydrogen from somewhere. We find that a lot of times in like biochem, for example, they don't care too much about the charge, drawing the charge, because there are protons floating around in biological solutions everywhere, and so it'll probably get protonated somehow. And so what do we have here? Here we have an OH double bond and an OH and a double bond. This is an enol. This isn't a dienol actually, or enodiol, whatever it is called, which means that we can perform tautomerization. And the key here is that we can tautomerize at carbon number 1 or carbon number 2. And depending on whether I tautomerize at carbon number 1 or 2 tells me what kind of glucose I get. So remember that the tautomerization is I'm going to get rid of the OH and the double bond and replace this OH back with a carbonyl. So if I tautomerize carbon number 1, that means that I can either get glucose or mannose depending on which way carbon number 2 orients itself. If the OH stays on the right side on carbon number 2, that means I get glucose, but if it switches over to the left side when I break this double bond, recreating a chiral center, if it switches over to the left side, I create mannose. Let's say carbon number 2 tautomerizes over here. Carbon number 2 tautomerizes. This is where the carbonyl will form. If the carbonyl forms here, that means I'm going to get fructose. And that was the end of our content review session last time. Let's continue. So, this was the... Ooh, I don't know how to number things. This was the Okay, I apologize for that. I had actually forgotten to scan one of the pages. Um, so that was the first reaction. The first reaction again was the tautomerization, excuse me, the epimerization and isomerization. The second reaction is the oxidation. So what does that mean? An oxidation reaction we know is when we're going to take OHs and make them into carbonyls. That's a classic oxidation reaction that we can do. So there are multiple ways that we can do oxidation reactions, and these can occur both in the open chains and in the rings. So both in the open chains and in the rings. So the first one that we can do is the Tollens and the Fehlings reaction, where we use either the Tollens reagent over here, as we can see, or the Fehlings reagent. So this is the Tollens reagent, and this is the Fehlings reagent. We can do those, and we know that if we do the Tollens reagent or the Fehlings reagent on an aldehyde, that's going to convert it into a carboxylic acid. It'll only convert this aldehyde into a carboxylic acid normally, but on glucoses we can actually convert both aldoses and ketoses into carboxylic acids. So on the aldose, so on a glucose or a mannose, we're going to convert this aldehyde. This aldehyde is going to get converted into a carboxylic acid. And on a ketose, what's going to happen is this CH2OH is going to get converted into the carboxylic acid. So this CH2OH is alpha, one carbon away from the carbonyl. So what you can conclude from this kind of reaction is that it'll always be C1. C1 is always going to be the carbon that gets turned into a carboxylic acid. We see in these scenarios both cases have C1 turning into a carboxylic acid. That's the first style of oxidation that we can do. The second style is for aldoses only. What we do is we convert it's the same reaction, but this reaction will only convert aldoses into carboxylic acids. As we can see here, the aldehyde is getting converted into a carboxylic acid, and we get no reaction with ketoses. That is the second style of oxidation that we can get. So, and again, remember that oxidation is going from alcohols to carbonyls, and from lesser carbonyls to greater carbonyls, or from aldehydes to carboxylic acids. The third style of oxidation that we can do is called a dioxidation, where, remember earlier I said that we can, up here, we can do all of these reactions to open and closed chains. So if this was a closed chain, a glucose or mannose, it would oxidize and get turned into an open chain. So the product here is always open chain. Over here, we see that I can do a dioxidation reaction, which means that I can take this glucose and I can oxidize two things. I can do it for both aldoses and ketoses, so for glucose, mannose, and fructose, it all applies. Here is this would be a glucose. Here is a glucose. I am going to use this reagent on it, so 60 degrees temperature, HNO3, and it is going to take my C1 and my C6, so C1 and C6, both are going to get turned into carboxylic acids. Up top, we only had just the top aldehyde turning into carboxylic acid, but over here, both C1 and C6 are turning into a carboxylic acid. Same thing for the ketose. So the ketose, I'm going to use the same reagent. This is the ketose in ring form, and both, again, C1 and C6 are going to get oxidized. In this reaction, both C1 and C6 get turned into carboxylic acids. Carrying on, the third style of reaction is the reduction reaction. So we are going from carbonyls to alcohols, and this one is very simple. There's just this reducing reagent, sodium borohydride, NaBH4, in water. That's all we need, and what that's going to do is that is going to transform, as going to take our aldehyde and make it into an alcohol. It works the same way for the ketone uh, carbonyl. When we're talking about the fructose, that carbonyl, that's a ketone, it'll turn that into an alcohol as well. Here is an example of a glucose in ring form. It'll turn this same carbon, we see this and this are the same product. It'll turn that carbon into an alcohol. So that means that this product always has to be open chain, because now my OH on carbon number 5 doesn't have a carbonyl to attack. So it's always going to be open chain. And this is not a carbohydrate because it is not a beta hydroxy aldehyde or ketone. I don't have an aldehyde or ketone over here. So that's the third style of reaction, the reduction reaction. Okay, let's move on to the fourth style of reaction, which is called oxidative cleavage, which is, as written here, the chopping of carbohydrates into little pieces. So I'm going to take the carbohydrate and I'm going to pluck off one carbon at a time. I'm going to, for use of a bad metaphor, I'm going to decapitate the carbon, the sugar, one carbon at a time. So I'm going to take off this one, and then if I continue, I'm going to take off this one, and if I continue, I'm going to take off that one. So these three are going to pop off, so on and so forth. So the chopping of the carbohydrate. How do I do that? So I take my sugar, and I count the number of carbons. So if I have a 6 carbon sugar, I'm going to need 5. So if I have a 6 carbon sugar, I'm going to need C minus 1, number of carbon minus 1. I'm going to need 5 of this reagent over here. And that'll give me oxidized cleaved carbons. And we'll show what that means. So if I have a 6 carbon sugar, I'm going to need 5, C minus 1. If I have a 3 carbon sugar, I'm going to need 2. So C minus 1 again. Let's show the mechanism for this and show what does it mean to do this, again, bad metaphor, decapitation process, and what are these oxidized carbons. So right here, I'm starting off with this triose right here, glyceraldehyde. And so it has 3 carbons. I'm going to need 2 reagents. Let's show the mechanism. This is an acid, and so that the basic oxygen of the carbonyl is going to pick up the proton, and that's going to make it more susceptible to attack. If this is an acid and I deprotonate it, it is now a base. So now this carbonyl is more electron deficient, so it's more susceptible to attack. So it's going to get attacked by this base, and I'm going to form this bond. Now, remember that this iodine right here, this I is electronegative, and its neighboring oxygen right here has electrons. So if this I is electronegative, it's going to want to absorb electrons into it. So it's going to want to take electrons. So it's going to steal the electrons from this oxygen. So they're going to react in such a manner. The I can't have more than 1, 2, 3, 6, 7 bonds. Here you can have up to 7 bonds, so that means that I'm going to get electrons resonating down here, or yeah, resonating down here, and this is what I get. So this is now the negatively charged oxygen that was over here. I have that right here. This is the positively charged oxygen that gave up its electrons. Excuse me, apologize for that. Gave up its electrons over to the oxygen, excuse me, the iodine over here. And so now this is positively charged. This is positively charged, and it doesn't like that to be positively charged, so this negative OH is going to deprotonate. It's going to deprotonate, and I get this little square structure over here, and then I get that. Through doing this deprotonation reaction, I have made this iodine electron deficient enough. It wasn't very electron deficient over here. It had a negative charge, which made it more electron rich. But I have made this iodine electron efficient enough that it says, I'm out of here. I'm gonna leave. I'm going to take the electrons from this bond and then dip. And I'm also gonna cut myself off over here. I'm gonna take the electrons over here and dip. I'm just gonna snip myself out. So what does that do? Let's take a look at this. Let's take a look at this and figure out what this does exactly. In doing this, so let's start here. Step number 1 is this bond breaking. This oxygen now only has one bond, and we know that oxygens want at least 2 bonds or want to have 1 bond and be negatively charged. So if this oxygen wants to have 2 bonds, what I'm going to need to do is I'm going to need to break this bond in order to satisfy this oxygen. And that's going to create a double bond right here with this carbon. So this is going to create a double bond right here. I'm going to break this bond and create a double bond, and that is going to create here a carboxylic acid, as we can see. And then what happens over here? So now this carbon now only will have 1, 2, 3 bonds. It needs a 4th bond. So this bond is going to break over. This group over here is going to say, I'm out. This group over here is leaving. This group over here is leaving. He's saying, I'm out. And that means that this bond is going to break and form a double bond over here. So now this oxygen again, it will be happy, and then this carbon now will be happy. But what is this? This is this aldehyde group right here. So this is what I meant by the decapitation process, right? I'm going to clip off the top of this, it's going to leave, and then I'm going to reform the aldehyde down here and then continue on with the mechanism with a second helping of CIO4. A second helping of CIO4 is going to break this bond over here. This group is going to leave, and then this group is going to get oxidized. See how this group that was originally over here got oxidized. This group over here got oxidized into this aldehyde over here. So I only showed like this beginning portion, but you guys can picture the rest of the mechanism. It's the exact same process where we get the protonation of this thing, and then it gets attacked by the iodine, and we get this reaction. So over on the very bottom of the page right here, I have it broken down how we can tell what our major product is if we are given a glucose. So any aldehyde, so let's mark this over here. Any aldehydes or CHOHs, which would be representative of this middle style OH. So any of those middle OHs are CHOHs. Those will all get transformed into carboxylic acids. They will all get turned into carboxylic acids. So if you're asked on a major product problem, they give you the glucose, I tell you oxidative cleavage, what is a major product? Any aldehydes you see, any of those in between CHOHs that you see, those are all going to get turned into carboxylic acids. Any CH2OHs, most of the time they're going to be on the bottom, or in the case of a fructose, it's going to be on the top. Those will get turned into aldehydes. If we do the mechanism for those, and we'll see that those get turned into aldehydes. And lastly, if I have any ketones, for example, if it's a fructose, the ketone will get turned into a CO2. So an example of that would be right here. This is a carbohydrate, and using my convention over here, I need to see, okay, so I have a CH2OH, and I have another CH2OH, so a CH2OH and a CH2OH. Those are going to get turned into 2 aldehydes when I perform this oxidative cleavage reaction. And then I look at, oh no, what happened there? Okay. And then I look at my ketone. Look at my ketone, and I say my ketone is going to get turned into a CO2 through this oxidative cleavage reaction. And then I look at what I have left here. I look for aldehydes, or I look for these in between CHOHs, and those are going to get turned into carboxylic acids. I have 3 of them actually. I have 3 of them, so I'm going to make 3. Oh, go away. I have 3 carboxylic acids. This is again a fructose, and so this is what a fructose will get oxidatively cleaved into. So moving on, we have these 2 reactions right here. So that was reaction number 4, the oxidative cleavage. Now reaction number 5 and reaction number 6 are essentially the same concept, is formation of esters and formation of ethers. So the product for these will always be cyclic, as we can see here. The product for these will always be a cyclic molecule. All I have to do is take my glucose, take my fructose, take my mannose, and either use 5 anhydrides, or I use 5 CH3Is, or 5 of this compound over here. If I use CH3Is, I'm going to need to use this as my solution, which is just base essentially. So if I use 5 of those, what I'm going to do is I'm going to transform all of my OH groups. All of my OH groups get transformed into here in this scenario. These are esters, and over here they are ethers on the bottom. So take a look over here. We look at the ring form. I have an OH here, have an OH here, 3, 4, 5. All of my OHs, I apologize for this being a little sloppy, but all of my OHs get transformed into esters up top. Over here, 1, 2, 3, 4, 5. All of my OHs get transformed into ethers now. They get transformed into ethers. There's really nothing more to this reaction other than I'm going to replace all of my OHs with an ester or all of my OHs with an ether. The thing about doing it with an ether, though, is if I take this compound, and I use acid and heat on it, I can transform the anomeric carbon, the one that I have starred right here, I can transform that anomeric carbon back into an OH, as we see over here. So what does this tell us? If I use heat, this is the only carbon that gets transformed. That tells me that this carbon is the most reactive. OH is the most reactive. This OH is a special OH because this OH, again, is the most reactive, and this OH tells us whether our glucose is called a reducing sugar or is it a non-reducing sugar. What is a reducing, what is a non-reducing sugar? So it's really simple. If we have a sugar with the anomeric oxygen having its hydrogen here, we see that the anomeric oxygen having its hydrogen, if it is an OH group essentially on the anomeric carbon only, then we call it a reducing sugar. That's all it is. If we still have an OH over here, it is a reducing sugar. Again, this is the most reactive OH. And we can see up here, so that means that this glucose, or excuse me, this structure over here would be a reducing sugar, whereas over here up top, I don't have any H's. I don't have an OH on my on my anomeric carbon. I don't have an OH on my anomeric carbon. Up top here, I have here an ester, and over here I have an ether. I have an ester and I have an ether. So these don't have, the O's don't have their H's on it. These are non-reducing sugars. So about the non-reducing sugar, again, remember that this OH is the most reactive. That means if I were to use only 1 mole of anhydride or only 1 mole of CH3I, if I were only to use 1 mole, this would be the oxygen that reacts. So this will be the first one, and if I were to only use 1 mole, everything else would remain in OH, and this would stay a CH. This would be the one that reacts. And what's special about the reducing sugar is that the reducing sugar is the one that links the polysaccharide chains together, and we are going to see that on Wednesday. And so, knowing that this OH right here, the anomeric OH, or what we consider to be the reducing OH, or knowing that this is the the most reactive OH, that means that a few things, like we said earlier, that if I were to react this with acid and heat, I would transform this one back into this oxygen back to an OH before I transform any of the other ones, and that also means that I can selectively make the anomeric carbon into an ether. So if I start out with my sugar in this form or in that form, right, and I react it with just with one equivalent of methanol in acid and heat, what that will do is that will selectively make the anomeric carbon the only carbon to get transformed into an ether. The other ones, since they're less reactive and I only have 1 molar equivalent, I only make that one into an ether. This reaction only works for ethers because it only works for ethers, um, and we can't make the anomeric carbon selectively into an ester, but we can for an ether. How that works. And so moving on, that was reaction number 5 and number 6, which is the formation of esters and ethers. Moving on to the formation of osazones. This reaction is not too complicated. This reaction, again, so we see over here, the product is always an open chain. And why is it an open chain? Well, we can see in the product what happens. So I can take any sugar that we've talked about so far, the glucose, the fructose, the mannose, all 3 of them, whether they're in open chain form or whether they're in ring form, they will all give me the same product. Here's what happens. I react this to form an osazone. I react any of these sugars with 3 of these benzene diamines, or whatever you want to call it. And what will happen is that my first 2 carbons will get bonded, as we see here. My first 2 carbons will get bonded to this diamine. That's all the reaction is. Just take the first 2 carbons, so take carbon over here, take these first 2 carbons, these first 2 carbons, these first 2 carbons, and then react them. And as we can see, the rest of the glucose, or excuse me, the sugar chain, the saccharide chain, it's all the same. This part is all the same on in all 3 of the open chain forms of glucose, fructose, and mannose. So that's why performing this reaction with a glucose, of mannose, or a fructose will all give you the same structure. So spend some time, take a look at the structure. All we're really doing here is just putting a double bond this attached to it. So take off these H's and then just double bond it to the glucoses at carbon number 1 and carbon number 2, and you'll be fine at carbon number 1 and carbon number 2, and you'll get the product. That's the formation of osazones. And now let's shift gears a little bit and talk about the synthesis of monosaccharides. So I can synthesize monosaccharides in 2 ways. I can take a very long carbon chain and chop it down to get myself back to 6 or 5 or however many carbons I want, or I can take little itty bits and piece those little itty bits together, so I can take 1 carbon from here, 1 carbon from there, and piece those together and get a 6 carbon chain. So either I can take a very long carbon and shorten it, or I can take very, very short carbon chains and glue those together. So first we're going to be talking about the Keilani, I'm going to call it the Keilani-Fisher synthesis. The Keilani-Fisher synthesis with the chain lengthening. That's what we're doing here. We are doing the chain lengthening. We are taking little itty bits and adding carbons to it. So how do we add the carbons to it? We're going to add the carbons by using this nitrile. This nitrile is what's going to give us our group here, our added carbon. So remember, so this is a negatively charged, so this is the ionic bond, this is negatively charged nitrile, good nucleophile. It's going to attack the electron deficient carbonyl. And as we see here, we have 1, 2, 3 carbons, and after this reaction we get 1, 2, 3, 4 carbons. So this is the now added carbon that we have, and as we can see here, I get 2 products, because again, this aldehyde can open up with the OH on the right or the OH on the left. It can open up both ways, so I get epimers. And then I perform a reaction that's new to us. We haven't seen this reaction before. This is called a partial reduction reaction, where I'm going to slightly reduce the nitrile here. I'm not going to reduce it all the way back into a primary amine. I'm just only going to slightly reduce it, partially reduce it into an imide. I'm going to reduce both of these groups into imides. And then what I'm going to do is a reaction that we've seen before. If we react imides with acid, I get my carbonyl back. So if I react an imide with acid, I get the carbonyl back. So the whole idea of the chain lengthening is I'm going to use the nitrile and tack on a carbon, partially reduce it to make it into an imide, and then transform the imide into back into the carbonyl, back into the aldose that it is now, and we can see that in our final product we have 1, 2, 3, 4, 1, 2, 3, 4 carbons. We added one carbon, and you can keep adding carbons by using the same method. So I can take another nitrile, sodium nitrile over here. I can take another one, tack it on, partially reduce it, and then add acid to it to transform it into an aldehyde, and I can just keep tacking on carbons, however many carbons I want, through this method. And lastly, this is the last thing we're going to go over today, the second method of carbohydrate synthesis, or monosaccharide synthesis specifically, is talking about chain shortening. So I'm going to take a long carbon chain, for example, and I'm going to cut off bits of it in order to form the chain or the the length of that I want for the glucose. So, or the saccharide. I forgot how to speak all of a sudden. So here we're starting off with glucose right here. Starting off with glucose, and I perform this reaction with it. What this reaction will do is, again, this is what we talked about earlier. This reaction right here is what we talked about all the way, where was it? Right here. This will oxidize the aldehyde part only. It won't oxidize ketones. So it'll oxidize the aldehyde. It won't oxidize C6. It'll oxidize the aldehyde into a carboxylic acid, and then we can see that, so I perform this step. This is my decarboxylation step. My decarboxylation step with some hydrogen peroxide, and I'm going to get this group to leave, and I'm going to reform my aldehyde over here. So this was 1, 2, 3, 4, 5, 6 carbons long. My final product is 1, 2, 3, 4, 5 carbons long because of my decarboxylation step. My carboxy group left. Let's look at the mechanism. So to start off the mechanism, we are going to perform this reaction, which is again transforming the aldose into the aldehyde into a carboxylic acid. We've seen this before. And now I'm going to focus my attention a little bit onto the peroxide. So remember that peroxide bonds are very weak, so they will split, and now I get two free radical OHs that I use in the reaction, I use in the mechanism. So what is going to happen? Here's how it's going to happen. Remember, I just formed my, oh, what is this? How'd that get there? I just formed my, transform my aldehyde into a carboxylic acid. This carboxylic acid has an H. This free radical is really reactive. It's going to deprotonate my OH right here. I'm going to get these fishhook arrows, and what that's going to do is form this C double bond O and then C single bond O to a free radical. This, again, free radicals are really unstable, and I'm also going to get water, of course, but this is really unstable. This oxygen doesn't want to have just one electron, it wants to have both of its electrons. So what is it going to do? It is going to find somewhere that it can pull electrons from. It's going to pull electrons from here. Remember, these bonds are 2 electrons each. It's going to say, I just need one more electron. Where am I going to get that electron from? It's going to pull the electrons from here, pull that electron from here, and form that double bond. So one electron is going to jump down, one electron is going to jump up. They're going to form that double bond over here. And what that means is, if I pull an electron from here, this bond has to break. So this bond breaks. And the decarboxylation step happens. This group ends up leaving because this bond broke, and I get my CO2. After this step, I get my CO2 that popped off. And what do I have here? This one electron has to go somewhere, so it'll jump down to this carbon. That free electron will jump down to this carbon again, and now this carbon is radical and it is unhappy. So what is it going to do? It is unhappy. So what it's going to do is it's going to find a way to get its electrons back. And it's going to do that by use of the second free radical OH that we formed. The second free radical OH is again going to deprotonate and form water. So it's going to deprotonate one of the electrons from here, from this bond, and the electron from this bond are going to link up in the middle and form a double bond here. So I get that deprotonation step. This is going to leave. Remember that a bond is formed of 2 electrons, so this OH is going to take this H. I'm left with my 1 electron over here that is going to link up in the middle with this free radical carbon and form that double bond. And what does that mean for me? If I form a double bond, I now have an HC double bond O. That is an aldehyde. So I reformed my aldehyde. I removed 1 carbon through this decarboxylation step and reformed the aldehyde through this final step over here. And now I can keep removing carbons through the same method. All I have to do is use this Br2OH, convert into a carboxylic acid, and then let the peroxides do their things, and then this group will leave, and then this group will leave, and then this group will leave, etc., etc., etc. And I can do that however many times I need in order to get the desired length of carbon chain that I need. So that is it for this content review session. I'm uploading it so that everyone can watch ahead of time so that no one falls behind, hopefully. I briefly skimmed through it because I had all the notes already written. Thank you for watching, and I will see you guys this Wednesday.